All right, we're going to get at least one video pumped out here for continuity, which is our very last lesson of the year. So without further ado, let's get going. Continuity and limits are absolutely connected. In fact, the definition of continuity involves finding the limits first. So the informal definition is that idea that if I have a graph, I would be able to take my pencil, put it down on the paper on the left side, trace my graph all the way to the right side of my graph without ever having to lift the pencil up. So informally, that's what we're looking at. Formally, it is a three-step process. Formally, it says if we want to know if a graph is a function is continuous at any particular point along the graph, we number one have to plug in that point. So if we want to know if the graph is continuous at x equals 2, the first thing we do is we plug in 2 into our function. Make sure we get an output. Make sure we don't get like divided by 0. Once we've confirmed that that's defined, then we look at the limit of the function at that same value. So again, we're using 2. So as x approaches 2, does it have a limit? If it has a limit, we say it exists. Then we move to step 3. Step 3, we have to compare the two values, 1 and 2. If the limit from step 2 is the same value as the function f of c value from step 1, then we say that we are continuous, and continuous at a particular point. So let's do an example. I know that was heavy when we first did it in class. It still seems a little heavy, so let's do an example. Here is a piecewise function. In fact, I'm going to pause and create that graph right now. So there we go. I just made it. There it is. All right. So there's our graph for x squared when x is less than 2, and 2x when x is greater than or equal to 2. So that's what it looks like. If we follow the red graph, we're going. We hit 2 and it's undefined, right? Because it says x is less than 2. It's that. Now we look at the blue one. That is our other equation, 2x. And we go 2x, and when we get to 2, we do have a value. So there's some good things happening. We take a look at this. Let's go through this step-by-step process. F of c is defined. So what that's saying is f of c being that 2 that we're focused at. So f of 2. What is f of 2? F of 2, well, we plug it into the bottom of our piecewise because that fits the domain criteria. So f of 2 is 4. Second step is find the limit. Okay, well, finding the limit involves looking at the limit as x approaches 2 from the left and from the right. Well, from the left, that would be plugging it into this equation here. So if we plug in 2, as we're approaching 2 from the left, our graph, we could even look at it graphically, as we're approaching 2 from the left, we're heading towards 4. As we're heading towards 2 from the right, we are in a different equation, but you notice we're still tending towards 4. So good news is the limit from the left, let me try that again. From the left, we're heading towards 4. From the right, we're heading towards 4. So in total, the limit as x approaches 2 is 4. So step 1, it is defined. Step 2, the limit does exist. The limit is 4. Step 3 says that f of 2 better equal the limit as x approaches c, which is 2, which is 4. So all things considered, we have checked step 1, step 2. 3 confirms that this is continuous. Okay. Now, we look at this again at example B. Let's look at this graph. Again, I'm going to pause this and get that graph ready. All right, graph is ready now here. So we're looking at a piecewise function where everywhere except 1, the graph looks like this. When x is exactly 1, it is exactly 5. So we look at our graph here, and it shows. Why didn't do that? There we go. It shows this. Green line is our top equation. going along until you hit x is 1. When x is 1, it's undefined. But we do have a value there. When x is 1, it does equal 5. But here, take a look. So is f of 1 exist? Yeah, absolutely. It's 5. The problem is our limit as x approaches 1. Well, graphically, I mean, we could look at this and say, okay, we're going to cancel this and cancel this, because again, we're not worried about at exactly 1. When the limit is, we're finding the limit of 1, like as x approaches 1, we don't care about the exact value of 1. We're asking ourselves what would happen as we approached x equals 1. And that's where we use this graph right here. So that graph says as we are approaching 1, we are looking at 1 plus 3. We plug in the 1 for this function, and the limit is 4. Now we can confirm that graphically. Going along from the right, as we approach 1, we're about at 4. From the left, we approach 1, we're approaching 4. So graphically we confirm it, algebraically we confirm it, but the problem is that f of 1 does not equal the limit as x approaches 1. Therefore, it is not continuous. Right? So that's your quick and dirty examples and explanations on continuity. We then go into, well, there's types of continuities, not for this video. I'm trying to get to the meat of some of this. So do pay attention and look at those types of discontinuities where your pencil would have to lift off the paper. But the other topic would be creating a continuous function. So let's say now, oh no, we know that we're not continuous. We have to figure out what value will give us a continuous function. So the example they're giving us here, it says, hey, we want our g of x to be piecewise where the second piece is some number. Well, that number needs to fill the void created by the hole in this graph here. So that is actually 2x minus 1 and x plus 3. So that's our numerator. Our denominator is x plus 3, x minus 3. So what you find is that the plus 3, x plus 3 on top and bottom is where our hole. So our hole is at negative 3, x is negative 3. In order to make that happen, let's find out what is the limit as x approaches negative 3. So 2x minus 1 over x minus 3, we want to know the limit of this as it approaches negative 3. So all I'm doing is I'm taking the original function, I factored it, and I've kind of reduced out the x plus 3's. And what will happen is, if I want to know the limit at negative 3, I'm going to plug it in and get over negative 6, and that's negative 3 times that, that's negative 7. So our limit is 7/6. If I were to graph this, what you would find is that we have a hole at x is negative 3, but the rest of the graph is continuous. Well, if I were to find the limit, which I did, the limit was 7/6. So if k were to be replaced as 7/6 when x is negative 3, we would fill the discontinuity, or the hole, and we would create a continuous function. So finding or creating continuous functions, it's as simple as identifying where the hole is, and once you identify what the hole is, you find the limit of the function at that point, and whatever that limit is the function value for k. Okay? We could look at another example here, but I am going to wrap this video up. We've talked about enough as it is, so the last thing we would do is talk about intermediate value theorem, but that is for another video.